In this video, we've got some more stoichiometry problems. These are a little bit more advanced in that they are just not your typical grams to moles to gram kind of problem. Some of these involve just moles, some of them involve solutions. So just a wide variety of problems here. So we've got an equation, iron plus hydrochloric acid makes iron 2 chloride and hydrogen gas. When a student adds 30 milliliters of 1.00 molar HCl to 0.56 grams of powdered iron, a reaction occurs according to the equation above. When the reaction is completed at 273 Kelvin and 1 atmosphere of pressure, which is STP, which the following is true. So first let's address this HCl that's in red. You know that molarity equals moles of solvent divided by liters of solution. And when you're dealing with stoichiometry, converting things to moles is always a great way to think about them. So if we can multiply both sides of this equation by liters, we'll find that the moles of hydrochloric acid is going to be equal to the molarity times the liters of solution. In this case, the molarity is 1 and the liters is 0.03 because this is in 30 milliliters, so we have to move that decimal 3 places. And you find that you have 0.03 mole of HCl. As for the iron in blue, you have 0.56 grams of iron, which we need to convert to moles, so we'll divide this by its molar mass since we've been given a value in grams. And iron has a molar mass of 55.85. Now you'll notice this denominator is basically 56. So you essentially have 0.56 out of 56. That is just going to equal 0.01 or 1/100th of a mole of iron. Now that we have some more simple looking answers, we can compare them using this balanced chemical equation up at the top. And in this we can see that 1 iron reacts with 2 HCl's. So our limiting reactant here is going to end up being the iron because 0.01 mole of iron, since the coefficient of iron is a 1 and the coefficient of HCl is a 2, you would need twice as much HCl. So 0.01 mole of iron would need 0.02 mole of HCl in order to react. And we have more than enough. So iron is our limiting reactant here. So now that we know that, let's go through these answers. A, HCl is in excess. That is true because iron is limiting. And 0.1 mole of HCl remains unreacted. Well, we just determined that to use up 0.1 mole of iron, you would need 0.02 mole of HCl. Since you have 0.03 mole of HCl, there would only be 0.03 minus 0.02. There would only be 0.01 mole of HCl left over. A says 0.1 instead of 0.01, so A is incorrect. B, HCl is in excess and 0.02 moles remain unreacted. No, 0.02 moles would be consumed, so 0.01 would be left over. B is also incorrect. C says that 0.015 mole of iron 2 chloride is produced. So again, if iron's our limiting reactant and 0.01 mole of iron go in, then we need to know how many mole of FeCl2 will come out. Well, it is a 1-to-1 ratio, so if 0.01 mole of iron go in, 0.01 mole of FeCl2 will come out, meaning we did not produce 0.015 mole of it, which means the answer must be D, but let's take a look at it. Again, your limiting reactant, 0.01 mole of Fe, and we're talking about hydrogen in this case. The mole ratio of iron is 1 iron for every 1 hydrogen, so you're going to wind up producing 0.01 mole of H2. Since we're at STP and we're producing 1/100th of a mole, we know that 1 mole at STP has a volume of 22.4 liters. Well, we're producing 1/100th of a mole, so we're going to have a volume 1/100th that. This will wind up producing 0.22 liters of hydrogen. In this problem, you have a 20 milliliter sample of 0.2 molar K2CO3, which is being added to 3.0 milliliters of 0.4 molar BaNO3(2). Barium carbonate precipitates. The concentration of the barium ion Ba2+ in solution after the reaction is what? So we need a chemical equation here. We've got K2CO3 reacting with BaNO3(2). Once these partners change, you're going to wind up with KNO3 and BaCO3, which precipitates out. And then to balance it, you need a 2 in front here of the potassium nitrate. So this is a solution problem because these are solutions of both. And it appears that you're going to add some K2CO3 to some barium nitrate to get a precipitate. But according to the question, some of that barium remains in solution. The only way that can happen, since this barium carbonate precipitates out, the only way there can be barium left over is if all the carbonate is used up. So we need to figure out how much carbonate will be, or how much barium will be left over after all that carbonate is used up. So when in doubt, let's mull it out. You have 20 milliliters of a 0.2 molar solution here. And again, we know that mole equals molarity times liters. So your number of moles of K2CO3 is going to equal 0.2 times 0.02, which turns out to be 0.004 mole of K2CO3 that's available in the solution. On the other solution, we have barium nitrate, and we have 30 milliliters of a 0.4 molar. So again, molarity, or moles rather, equals molarity times liters. So your molarity of 0.4 times a volume of 0.03 liters. And we wind up having 0.012 mole of BaNO3(2). So obviously we have more barium nitrate than we do potassium carbonate, and we can tell from our balanced equation up top there's a 1-to-1 ratio. So we are trying to figure out this barium ion. Well, if we think about this here in blue, for every 1 BaNO3(2) that dissolves, you're going to get 1 Ba2+ ion produced. So by having 0.012 mole of barium nitrate, you're also saying that you have 0.012 mole of Ba2+ ions. The same can be true here. For every 1 K2CO3 that goes in, 1 CO3 comes out. So you're going to have 0.004 mole of CO3. So let's think about what's doing the reacting here. This barium on the right is going to react with the carbonate in red on the left to produce barium carbonate. So if you wanted to think of this as a limiting reactant, you don't have enough carbonate to react with all of this barium. In fact, if you subtract 0.012 minus 0.004, you'll see that you have 0.008 mole of barium 2+ ions that never reacted with anything. They're still just hanging out in that solution. So the question, what's the concentration of that barium ion? Well, you have 0.008 moles. Now we need to know what is the volume of this container. Well, initially you had 20 milliliters, but you added that to 30 milliliters. So that's a total of 50 milliliters. You have 0.008 mole of barium in 50 milliliters. So in order to find the molarity, or the concentration, molarity is moles per liter. You have 0.008 moles in 0.05 liters, which comes out to be 0.16 molar. So B is going to be our answer there. All right, in this next one, a 2 mole sample of F2 reacts with excess sodium hydroxide according to the equation above. If the reaction is repeated with excess sodium hydroxide but with 1 mole of F2, which of the following is correct? So at first you put in 2 moles of F2. Now we're only putting in 1. So we're halving the number of reactants going in. So A says the amount of OF2 produced would be doubled. It doesn't make much sense to put in more reactant, or less reactant rather, and get more product out. So A cannot be our answer. B, the amount of OF2 produced is halved. Yes, if you half your limiting reactant, you will get half as much product out. So B has to be our answer. And again, C and D don't make any sense. You can't maintain the same amount of product coming out if you halved the reactants going in, and D, you certainly can't get more if you put less in. So this next one, a titration experiment based on the equation above. 25 milliliters of acidified Fe2+ solution requires 14 milliliters of standard 0.05 molar MnO4 1- solution to reach the equivalence point. So the equivalence point just means at that point there are equal number of moles of both. So what's the concentration of the Fe2+ solution then? So you could actually work this one out by converting to moles and comparing the moles and seeing everything there. But in a titration like this, it's much easier just to use MV equals MV. And again, this is derived from the fact that molarity equals moles per liter or volume. So moles equals molarity times liters or volume. So this right here is equivalent to this, which has to be equivalent to the other side's moles because we're at the equivalence point. So in a titration, just use MV equals MV, and you don't even have to worry about converting your milliliters to liters. So on the left side, our molarity is unknown. We're looking for the concentration of our iron, but we know that we had to have added 25 milliliters of that iron. The moles have to equal the other solution here, which has a concentration of 0.05 and a volume of 14. So just by solving for x here, you'll find that the concentration of the initial substance was 0.028 molar, which is option C. In this one, you have a 100 milliliter sample of 0.1 molar MgCl2 and a 100 milliliter sample of 0.2 molar sodium hydroxide. And it says that MgOH2 precipitated. If the experiment is repeated using solutions of the same molarity, but the volume changes in volume will double. I'm sorry, which of the following changes in volume will double the amount of MgOH2 produced? So we're trying to double this product right here. First, we need to evaluate which of these two is the limiting reactant. Since you have a 100 milliliter sample of each of them, and the Mg2 is half as concentrated as the NaOH, you have half as many moles of MgCl2 as you do NaOH. However, the NaOH has a coefficient of 2 out front, so it's being consumed twice as quickly. So even though you have twice as much NaOH, you are using it twice as quickly, so you're actually going to run out of both of these at the same time. So knowing that, let's look at the answers. And again, we're trying to double the MgOH produced. So, A, using the same volume of MgCl2, but twice the volume of NaOH. That's not going to help you because you've doubled the amount of NaOH, but you haven't changed the MgCl2. And since the MgCl2 and the NaOH were both going to run out at the same time, they are both limiting reactants. So doubling one limiting reactant without doubling the other isn't going to help you produce any more product. For B, using twice the volume of the MgCl but half of the other limiting reactant, that doesn't make sense. That's going to produce you less substance. C, using twice the volume of MgCl but the same volume of NaOH, again, doubling one but maintaining the other is not going to produce any more substance. So using twice the volume of both must be our answer. In this one, we've got a more straightforward mole problem, hopefully more straightforward. If 0.4 mole of H2 and 0.15 mole of O2 were reacted as completely as possible to produce water, what mass of reactant would remain? So we have H2 reacting with O2 to produce water. We'll just quickly balance this. You need 2 oxygens on the right. Now you need 4 hydrogens on the left, and it's balanced. You're putting in 0.4 mole of this and 0.15 mole of this. In order to determine the limiting reactant, let's think about which one's going to run out first. If you only have 0.15 mole of O2, the H2 is being consumed twice as quickly because of the coefficient of 2 out front. So you're going to need twice as much. You would need 0.3 mole of H2 to react with all of the 0.15 mole of O2. So with that being said, oxygen is your limiting reactant, and you're going to wind up using 0.13 mole of hydrogen. So when this reaction's over, you will have used all of your oxygen, but you will have only used 0.3 of your 0.4 moles of hydrogen, leaving you with 0.1 mole of hydrogen. Now the question asks what mass of hydrogen or what mass of reactant would remain. Well, the molar mass of hydrogen, since it's diatomic, is 2.016. We only have 1/10 of a mole though, so we're only going to have 1/10 that mass. There will be about 0.20 grams of hydrogen left over, which is A. In the next problem, you have 8 grams of N2H4, and they give us the molar mass, and 92 grams of N2O4, and we're given the molar mass, and they're mixed together. What's the maximum mass of H2O that can be produced? So, again, if you can see that we have 8 grams out of 32, well, 8 out of 32 means that we have 0.25 mole of N2H4, and we have 92 grams of a substance that has a molar mass of 92 grams, so we have 1 mole of N2O4. So what's the maximum mass of H2O that can be produced? We have to determine what's our limiting reactant. You can see that the N2H4 is being consumed twice as quickly. So we're definitely going to run out of N2H4 first. But this is a little bit tricky here. If 0.25 mole of N2H4 go in, you're only going to use half as much N2O4 because its coefficient is half that of N2H4. So that means instead of using 0.25 mole, you're only going to use up 0.125 mole of the N2O4. Now, I'm not actually sure that's necessary to know for this problem because I wasn't paying all the attention that I should. We're just looking for what's the maximum mass of H2O that can be produced. Well, 1/4 of a mole of N2H4 is going in. For every 2 of these that go in, 4 waters are produced. So 0.25 mole of N2H4 will produce half of a mole of water. And since water has a molar mass of approximately 18, you're only getting out half of that mole, which means you only produce 9 grams of water. And in this one, we've got another reaction. What mass of HF is produced by reacting 3.0 times 10 to the 23rd molecules of H2 with excess F2? So we don't really care about the F2 in this situation, it's in excess. But since 6 times 10 to the 23rd is a mole of molecules, and we only have 3 times 10 to the 23rd, we only have half of a mole of H2. So if half of a mole of H2 goes in, you'll get out twice as much HF according to the coefficients. So this will result in 1 mole of HF being formed. So we just need to know what's the molar mass of HF, and we're going to approximate this. Hydrogen's about 1, fluorine's about 19. So this has a molar mass of about 20 grams, and since we're making 1 mole, our mass will be 20 grams.